an application of systems of linear inequalities are problems called linear programming. Our objective is that we can apply linear inequalities to optimization problems. Linear inequalities is a business application where we use these graphs to find minimums and maximums in things like profit and cost. So what we do is we call the system of linear inequalities the constraints. We graph them. The region that's formed by is called the feasible region. The vertices on that region are what are the possible optimization points, the minimums or maximums, and then we use that with a profit or cost statement to find either maximum profit or minimum cost. So let's start off with this and graph this system. So we're going to do this one starting with the 6. We're going to go down 2 over 1, down 2 over 1, down 2 over 1. And then we're going to draw that as a solid line. And this graph is going to be below the graph. So I'm going to just mark that like that so I know where I'm going to be graphing it once I get to shading the entire region. The next one, x is greater than or equal to 1, is just a solid vertical line at x equals 1. That looks like this. And we're going to go greater than it, so on this side. So far we have this region down here is the overlap of those two graphs. And lastly, we're going to go with y is greater than or equal to x minus 1. Start at negative 1 here. Go up 1 over 1, up 1 over 1, up 1 over 1. Okay, and then we draw this, and we get a solid graph. That again, this one we're going to shade above it. So we're going to have this region where we would shade right in the intersection of all those, which is this region in here. This is called the feasible region. That feasible region gives us all the points that satisfy that system of inequalities, the constraints. Now, we want to find the vertices of each of these. So this feasible region, the vertices are these points here. This point's not hard to find. It's at an x value of 1 and it's a y value of 4. So it's a pretty quick one to find. This one also is pretty easy to come up with. It has an x value of 1 and a y value of 0. It's this one that's not quite as easy to find. It's the intersection of this first one and the third one here, where if they were equal, we find the intersection. So I'm going to actually use that system of equations, negative 2x plus 6, and y equals x minus 1. I'm going to solve that system to find out where this x and y ordered pair is. So I'm going to substitute this in for the y right there. So I get x minus 1 equals negative 2x plus 6. I'm going to add 2x to both sides. I'm going to add 1 to both sides, and so I get x equal to 7/3. So the x value here is 7/3. Okay? Now, when I plug that in, or substitute that in, I can do it to either one. So if I put 7/3 minus 1, that's going to give me 4/3 for the y. So that ordered pair, this vertice, that corner of the feasibility region, is one of the possible min-max points. So we got to test all of these. We got to go with, we're going to take 1 comma 4 as one possibility, 1 0 as another possibility, and then 7/3 comma 4/3 as our third possibility for minimums and maximums. Now, you're given usually in a situation whether this is cost or profit. And if you have cost, you'll want to minimize it. If it's profit, you want to maximize it. The only possible mins or maxes for these equations are at the corners. And the reason why is that this is a linear equation, and a graph of a line, if you were to draw it and have it approach this as it moves toward it, the first place it would hit, it would be one of these corners, and the last place it would hit would be one of the corners. So the corners are always going to be where the minimums or maximums first or last places they hit. So let's go ahead and substitute these in. If I put in 1 and 4 into this profit, for this one I'm going to get profit equal to 3 minus 4, it gives me -1. So I'm going to have that be a negative profit. Not very good. So this profit's going to be 3 times 1 is 3 minus 0 gives me a 3. Okay, not so bad. And this last one, I'm going to put in 7/3. 7/3 times 3 is going to be 7 minus the y, which is 4/3. So this is the same thing as 21/3 minus 4/3 is going to give me a total of 17/3. Okay, so that 17/3, notice 17/3 is a little more than 6. This would be my maximum profit, and this would be the point that would give me the maximum profit or optimize the profit in this case. So now let's look at a specific optimization problem. This problem is the Fractal company is converting to laptops and to tablets. They have to order at least 20 tablets and 30 laptops, but must have at least 100 machines programmed in a week. The IT staff has at most 1,400 possible hours to program because they've got limited staff, so they can't be programming more than that. And a laptop takes 10 hours to program, while a tablet takes 7. Let's put that into constraints. So let's let L equal number of laptops and T equal number of tablets. So I'm going to let this here, I'm going to do it alphabetical, so I'll have L here and I'll have T up here. So it says that they must order at least 20 tablets. So tablets have to be greater than or equal to 20. 30 laptops, so L has to be greater than or equal to 30. And they have to have at least 100 machines. So if you put them together, if you have T plus L, you have to have greater than or equal to 100. Okay, because they must have a lot of staff that needs those laptops, or if they're selling them, they might have to get a lot of order out there. Okay, so the IT staff has at most 1,400 possible hours, so the programming hours must be less than or equal to 1,400, and it takes 10 hours to program a laptop, so it's 10 times the number of laptops. And then we've got to add to it 7 times the number of tablets because it's 7 hours for every tablet to do it. So if you put all the hours to do the laptops and the tablets, it has to be less than or equal to 1,400. Okay, so now we've got a system of inequalities that we can graph to see what our feasibility region is. So let's go ahead and start here. So for L, it has to be greater than or equal to 30. So here's 30. So I'm going to draw a vertical line here and say that it's got to be greater than or equal to 30. Then it has to be, T has to be greater than or equal to 20. So I'm going to go here at T, draw that out here. So it's going to be greater than or equal to 20. Now T plus L has to be greater than or equal to 100. So if we do the intercepts there, both of them, if I put in 0 for T, I get 100 for L. If I put in 0 for L, I get 100 for T. And so that's just a line that looks like this. It's a solid line also. And this is going to be graphed above it. If you put in 0, 0, it doesn't work, so you have to put on the other side of it. So far I've got this region out here that's not bounded, but now this is going to bound it. So if I do each of these, like if I graph this, if I put in 0 for T, for L I get 140, so that would be right here. And if I put in 0 for L, for T I would get 200, so that would be up here. And I connect those intercepts when I graph those. So I go down like that. That's that line. And again, this one's going to be less than it. If you put 0, 0 into this one, it does work, so we're going to graph on that side. So my feasibility region for this one is this whole region bounded to the right of this, above this one, and below that. So if you put all those together, you get this region for my feasibility region. Now, the minimums and maximums have to occur, the optimization corners there, the vertices of it. So if I look at each of these vertices, okay, some of these are not as hard to get. This one is going to be, it's going to have a t value here of 20. Okay, and if I put 20 into this one here for t, I'm going to get, so let's just do a quick calculation. I'm going to get 10L plus, if you put in 20, you get 140 is less than or equal to 1400. I'll just make it equal because we're trying to get the number there. So if we were to solve that for L, subtract 140 and divide by 10. So 1400 minus 140, and then get that number, that's 1260 divided by 10 is 126. So this is 126 for that point right there. Okay, let's do this point up here. This has an L value of 30. I'm going to again put it into this one. So 10 times L, 10 times 30 gives me 300 plus 7t is going to equal 1400. So let's go ahead and subtract 300 from both sides. So 7t would equal 1100. Divide by 7. So if we take 1100 divided by 7, we get a decimal. So what we have to do here is realize that this number here is going to be just a fraction of 1100 divided by 7. Okay, which is not a nice number, but it helps us in this problem at least to get what the corner is. This corner here, that has a L value here of 30. And if I put that into this one's equation's a little easier. It's t plus L equals 100. I get 70 for the other one on this line. And then this vertex there, that one is going to have, notice it has a L value, the first one, of, it's going to have, I'm sorry, a t value, because it's got this value here is at 20. And notice 20 plus 80 gives me that 100. So what we can do is now substitute all of those in. What I'm going to say is the cost is $500 per laptop, and it's going to be $300 per tablet. What we want to do then is to minimize cost. So our cost formula is going to be 500L plus 300T. We would like to minimize that. So if we take each of these ordered pairs and we substitute them in, I'm going to start with 80, 20. If you go for the cost here, you substitute that in, and you're going to get 500 times 80, the L, plus 300 times the T, which is 20. And that gives me cost of $46,000. Okay, let's put in this one up here. I'm sorry, this one here, 3070. Putting in 3070, the cost will be put into this equation, 500 times 30 plus, now we're going to do 300 times 70, and we get for that one a cost of $36,000. So already we have a lower cost. This would be a better answer to the question. We're trying to minimize cost. Okay, now the next one, let's do this 126, comma 20. Now these are pretty large numbers, so I'm guessing that the cost is gonna be higher. This would be more points where we might maximize profit. If these values had been how much profit we make on each of them, then we probably would have one of these two, but let's just check them out just to see. So 500 times 126 plus 300 times 20, and we get $69,000. Okay, quite a bit more. And then lastly here, if I take this one, 30, comma, and then 1100 over 7, that's 157.142, by the way. So it's likely we would just do 157 because you'd want to make it one less. So I'm going to use, instead of that number, because we're doing cost, 157 instead. So I'm going to go cost is 500 times 30 plus 300 times, and I'll use the 157 instead of the fraction because that's less than. That would be cost of $62,100. So if you notice here, our lowest cost is this one. So if we're trying to minimize cost but meet all these requirements, what this is saying is that we should do 30, and remember it's L laptops, and 70 tablets at a cost of $36,000. Okay, and that would be the solution to that optimization problem. So what you do is you come up with the constraints from the word problem, write out those inequalities, graph the feasibility region, look at the corners for your minimums and maximums, determine what your cost or profit statement is, minimize cost, maximize profit, and solve your problem.